We're now ready for another exciting technical presentation by Giuseppe Sgoluppi, Vehicle Dynamics, Simulation and Performance Engineer at Automobili Lamborghini, and Alfredo Corollaro, R&D Coordinator Real-Time and Vehicle Modeling at Bridgestone EMIA. They will present a specific use case where Automobili Lamborghini and Bridgestone optimize the coupling between the suspension setup and the tire dynamic footprint through a fully virtual approach using finite elements modeling and driver in the loop.
Good afternoon, everyone. I'm Giuseppe Sgoluppi from the Vehicle Dynamics team of Automobili Lamborghini. And today, together with Alfredo Corollaro from Bridgestone EMIA, we're going to talk about a joint activity done during the development of the Huracan STO. The activity aimed at the optimization of the tire dynamic footprint in specific condition. The Huracan STO had very challenging development targets and timeline, and the only way we could achieve this target on time was to go virtual as much as possible. Here I give you a short overview about the STO. STO stands for Super Trofeo Omologata, which means that is a sort of homologated version of the Huracan that takes part in the Lamborghini Super Trofeo Championship. Like the other model of the Huracan family, it has a V10 engine with 640 horsepower with a rear-wheel drive configuration. The natural environment of the STO is the truck. That's why it has an enhanced aerodynamic package with adjustable rear wing to regulate the downforce. The lightweight design and the CCMR brake disc allow the STO to reach excellent performance in acceleration and braking, as well as in the lateral dynamics. As I told, it's a rear-wheel drive car, unlike most of the models from Lamborghini, which are four-wheel drive. That's why, from the very beginning, the tire development focused on enhancing the traction capabilities, especially in the combined phase, such as, for example, the exit from low-speed corner. Talking about the workflow, on one side, we have the VI car real-time full vehicle model from Lamborghini of the Huracan STO, which fortunately was available from a very early stage, since with most of its subsystem validated, because the STO shares some subsystem with the previous model of the Huracan family. And on the other side, we have the tire wheelstar prototype by Bridgestone. The meeting point between these two worlds is the driver in the loop. The driving simulator has been used mainly in two phases. At the beginning, we used the driving simulator to explore with our test driver the vehicle balance and the behavior on different situations on the truck. And it was very important for us to have a validated suspension system and to use our reference test driver that could perform on the simulator the exact same maneuver that he usually does on track for this kind of test. And from these maneuvers, from this test, we extracted data that have been provided to Bridgestone to perform their virtual prototyping and design, as Alfredo will explain in details later. The driving simulator has been then used to close the loop at the end of the activity to assess, and we were able to assess several specs coming from the virtual prototyping, and way before than the actual physical prototypes were available on track. Talking about the combined traction capabilities, we took into account as use case the hairpin at the turn 5 at Nardo Technical Center. Maybe you saw the truck this morning, the DM400 test. For those who are not familiar with the hand-in truck at Nardo, it's low-speed corner with a very small curvature radius, which is critical in the turn-exit phase. On the right, we can see the situation that we have in the first test at the driving simulator. Here we see the STO with a reference Wiltor tire, and another model of the Huracan family, which is which has a four-wheel drive configuration. We can see on the upper plot, for example, that even though the STO has a higher speed at the corner apex, it is critical on the turn-exit phase, where, of course, a four-wheel drive is much more effective. And from the driver perspective point of view, we can see in the two plot below, where we have the steering wheel angle and the throttle demand, that with the STO, the driver is not able to go hard at full throttle, flat out, until he has almost completely realigned the steering wheel. And on the other side, the four-wheel drive, of course, is much more effective in this phase. Here we see the same situation from an acceleration point of view. In the plots, you have the longitudinal acceleration versus the speed. We can see in the upper plot, we have the complete lap at the handling track. We can see that the two cars are similar in most of the phases, and the area where they differ most is the low speed range. In the plot below, we see I have plotted just the points relative to the hairpin, to the turn 5, and it's very clear that at low speeds the STO has lower performance much lower performance than a four-wheel drive reference in this condition. Considering the above-mentioned use case, that we can see also in the GG plot on the right, where we have in the gray the full lap, and on yellow just the turn 5 highlighted. We extracted from several laps the tire actual working condition, such as in terms of normal load, for example, and the characteristic wheel angle, such as camber and toe with respect to the road. And this data have been provided to Bridgestone to make their analysis. And before giving the floor to Alfredo, I would like to stress a bit more the concept that we put a big effort on getting the actual tire working condition in different situations. And that was possible thanks to the driving simulator and our test drivers. And so we went in a very sharp detail of all the phases of the tires in every phases of the corner. And here we can see from a qualitative point of view, let's say, the difference of considering a tire in a normal static condition, so with the static load applied on the tires and the static setup angles of the suspension, compared to a dynamic situation where the tire dynamic footprint are the results of the load transfer, and the actual angles and states acting on the tire are the result of the suspension kinematics, the vehicle states, and the forces and moment acting on the wheel. And with this, I'll leave the stage to Alfredo.
Thank you. Thank you, Giuseppe, and good afternoon all. So, to capitalize what we have done in the first part of the activity, we leveraged our capabilities on virtual tire development. Here we are reporting the workflow that we adopted. So we started from a Bridgestone existing spec used as a reference, of which we built the digital twin, so the virtual replica of the tire. And then we entered the actual virtual tire development loop in order to optimize the tire and building several trials, several specs, as we are going to see in the next slides. So let me explain what we did specifically, so exploiting the data that we collected during the first session on the driving simulator. We knew the actual working conditions of the tire in specific and different parts of the truck. With those data, we used those data to optimize the shape of the mold of the tire with the targets of optimizing the contact pressure distribution, of increasing the contact area in those specific cornering conditions in in order to get an higher grip level experienced by the driver, by the tire, sorry, in a fully virtual environment. We tested several trials. Here we are reporting just some options as an example. And among all of them, we selected the best option of all that has been translated directly into the final design of the mold for the Potenza Race product. Then, still leveraging on one of our capabilities, capable to predict the force and moment of a tire, still in a fully virtual environment. Here, for example, we are reporting a direct comparison between the measurements acquired on our flat track, reported in blue, and compared with the output of the simulations reported in orange. And in addition to the two sizes of the Huracan STO, we have also reported the 16-inch, just as an example, to highlight that we use this tool for any type of tire, for any type of size. Using this tool, we fitted the MF tire models of all the virtual specs that we designed during the optimization phase. Because once the mold has been defined, then we also performed, still in a fully virtual environment, the optimization of the construction of the tires. So as I said, thanks to this tool, we built the MF tire models of all the virtual specs, and then we moved one more time. If we can go next, please. Okay, thank you very much. With all the MF tires, we moved one more time on the driving simulator to subjectively assess all of them. We tested more or less 70 different combos front-rear in order to get the best balance of the vehicle and to improve the overall performance along the whole track. Only once the best combo has been identified, we finally built for the first time the first physical prototypes of the tires. And then the outcome of the whole activity has been fully confirmed once on track on the real vehicle. Now I leave the stage one more time to Giuseppe that will explain the outcome, the details of the outcome from Lamborghini, let's say, point of view. Please, Giuseppe.
Okay, here I want just to give you an idea about the result from the vehicle dynamics point of view. And here there is the situation, the pre-optimization with the referent tire spec that we saw in the previous slide. And this is the situation that we have after the optimization. Of course, now we are focusing on a specific aspect, which is the combined traction for the rear axle, but of course the tire optimization involved also other aspects. But from considering the traction point of view, we can see that from the speed profile on the top right, that now the performance are comparable with a four-wheel drive almost, and that from the driver point of view, for example, that the driver is able to go on the throttle harder earlier, and even when the steering wheel angle is still not aligned, let's say. And also on the left, we see the same plot as before with the longitudinal acceleration, and we can see also that the optimization was able also to increase the corner apex. And then from the acceleration point of view, it's I think that the optimization went in the right direction. So I leave the stage one more time to Alfredo for the last conclusion.
Thank you. Okay, I'm going to conclude the presentation, and please do let me make just some remarks. The virtualization of the mutual processes allowed us to be very fast in responding to the requirements by Lamborghini. Thanks to the virtualization, we saved up to 75% of the time during this specific development. Furthermore, let me highlight that we provided Lamborghini with the virtual tires of non-existing products at that time. And for sure, the process has been sustainable since it allowed to reduce the physical test on real vehicle. We saved up to 900 kilometers, so reducing the CO2 emission, also thanks to the saving of more or less 200 experimental tires that have been not built at all thanks to the virtualization. From this point of view, the driving simulator has been an important and essential brick during the full virtualization of the process. Thank you. Thank you very much.